Welcome to the fabrication project of a highly intensive cooling device. The mechanics dismantle the internal components of an old water purifier's plastic casing to make room for the new system. The metal panels are being coated with silver gray electrostatic paint for complete rust prevention. 4 perfectly even coats of spray paint flawlessly restore the alloy structure, prepping it for the cooling module. An AC exhaust cooling fan is test fitted onto the back panel to accurately mark its outline. The fan guard's diameter is marked with a red pen for precise measurement, preventing air leaks during operation. An angle grinder with a high-speed cutting disc quickly cuts out the plastic circle, although leaving behind a few burrs. The remaining burrs are scraped clean with a utility knife, leaving a perfect chamfered edge to act as a mounting bracket for the exhaust fan. Pilot holes are precisely drilled. The cooling fan is now fitted tightly, ready to serve as the heart of air circulation. Moving on to the standard household standing fan, the safety guard and blades are removed to integrate the direct heat exchange coil. The pure copper pipe is being bent into a concentric spiral shape to increase the surface area for cold air contact. The mechanic uses plastic zip ties to firmly secure each coil of the pipe to the fan guard, preventing resonance and vibration. This rigid fixing technique prevents the risk of the copper pipe cracking under the circulating pressure of the compressor's refrigerant gas. The center coil has a very narrow bending radius. Bending it by hand would crush it, completely blocking the refrigerant flow path. Using PVC pipe fittings to act as bending jigs makes sharp angles extremely precise, preparing for the compressor connection. Returning to the cooling machine module, gray silicone acts as a waterproof sealant, completely covering the metal grooves. A mica partition is pressed firmly onto the glue, forming the watertight base of the tank, to prevent cooling fluid leaks. The main load-bearing frame is being assembled by fixing the aluminum side panels directly to the chassis base. Please prompt to continue generating part 2 of the translation. The horizontal crossbars are screwed in, forming a solid block to support the load of the entire system. Every metal detail is aligned to ensure the machine base does not vibrate when the motor is running. The frame structure surface is gradually finalized, ready to receive the components that control airflow and fluids. A bead of silicone is applied along the edge of the partition. The insulated aluminum composite panel is fitted closely to act as an airtight wall. A cordless drill continuously drives self-tapping screws, firmly reinforcing the aluminum panel to the frame to create a complete outer shell. For a refrigeration copper pipe bending technique, a compressed air can is used as a cylindrical mold to coil it into a hollow spiral spring shape. The coiling process requires a consistent pressing force to ensure the pipe's cross-section is not crushed, maintaining the flow of the refrigerant. A plastic flanged pipe continues to act as a fulcrum, helping to bend the tail end of the copper pipe straight through the center of the spiral coil. A smaller capillary tube is also bent in parallel. This will be the evaporator or condenser assembly, compatible with the refrigeration compressor. On an old Toshiba refrigerator compressor, the mechanic uses an angle grinder to cut off the crimped seals, opening the gas, charging, and discharge ports. Two decisive grinding maneuvers ensure no iron filings fall inside the piston chamber, protecting the fragile reed valves. 3 copper spiral coils are placed on top of the compressor, using a high-temperature hot glue gun to tack them temporarily and shape the structure. Moving to the cooling machine casing, the honeycomb paper cooling pad is slid into the air intake groove at the rear. A mini-submersible pump sends water up to the distribution system, wetting the entire surface area of the paper pad to create an evaporative cooling effect. A rotary dimmer switch is installed in series with the two 20 volts power circuit to independently control the pump system. The wire strippers are operated with extreme skill, cutting away the fragile PVC insulation, preparing to connect the stranded copper wire cores. The electrical joints are tightly twisted, ensuring the conducto U0072 cross-section prevents arcing and overheating under load. Electrical insulation tape, black PVC tape, is wrapped tightly diagonally to cover all conductive metal parts, preventing short circuits and leaks. The fan guard and copper pipe heat exchanger are reattached to the fan motor shaft, preparing for assembly. The fan guard integrated with the copper coils is assembled. The entire system is placed on a mobile wooden base. The refrigeration compressor is securely fixed to the wooden base using a cordless drill and high-strength screws. The capillary tube is neatly coiled around a PVC core. The end of the spiral coil at the fan guard is widened to fit tightly over the capillary tube, creating a closed loop. Heavy-duty 2-part epoxy is used. Upon chemical reaction, this mixture hardens like steel. The epoxy mixture is carefully applied to the high-pressure joints to completely seal the connection points. Silence. 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 Instead of using refrigerant gas, the compressor is modified into a high-pressure circulating liquid pump. The compressor's power supply circuit is being wired. Heat shrink tubing is heated to snugly protect the copper cores. Flexible PVC pipes connect the machine base to the fan unit, ready to pump the cooling fluid entirely through the coils. The top cover of the DIY cooling tower is removed to reveal the fluid chamber and cooling pad. Two, clean water is poured directly into the cooling chamber. This fluid acts as an intermediate heat transfer medium. 3. Ice is added to significantly drop the water temperature, and the chamber lid is tightly closed to lock in the cold. 4. The cooling tower module is now powered on, and the switch is activated to test the forced airflow.
The high-capacity exhaust fan starts up, forcefully drawing hot air through the wet cooling pad. The evaporative heat absorption process occurs instantly, blowing out an icy mist to cool the environment. The evaporative cooling system is moved and placed next to the computer setup for actual load testing. Power is connected. The fan motor roars, and the space instantly cools down to an ideal temperature. It has extremely powerful cooling capabilities, even outdoors, with the emitting mist completely dissipating the heat radiation. Returning to the independent refrigeration compressor system, a copper flare fitting is tightly screwed onto the gas charging valve. A specialized refrigerant cylinder is connected, and high-pressure refrigerant gas is fully charged into the cycle.
The 220 volts power supply is activated for the compressor, and the internal piston begins continuously pumping the refrigerant. The twisted copper coil on the compressor acts as a condenser, cooling the hot gas discharged from the compression chamber. The liquid refrigerant passes through the capillary tube, drops in pressure, and suddenly becomes freezing cold as it reaches the fan coil. The workspace now maintains an optimal temperature, proving the success of this cooling project.